Hello everyone, thank you for joining us for Handmade Hero, the show where we code a complete game live on stream, and we are kind of in some interesting territory now. Probably going to be kind of fun, depending on how much GPU nonsense we hit, but we implemented lightning lookups yesterday, and we kind of get to start playing with those today a little bit, which should be kind of fun and interesting, I think. Let me kind of show you where we're at, just so you have some sense of it. I will run the game here. And what you can see is we've striped our voxel light lookup with red, green, and blue colors, so you can kind of see inside the lighting volume those stripes, which are just kind of a debug view for us, that let us know that the voxel lookup on one of our voxels is working properly. That's great, because that means from here on out, we can play with this a little bit and sort of start to see, we can get some sort of ballpark opinion of how slow it will be if we actually do 6 full voxel lookups for complete lighting. Right now we're only doing that 1. I mean, technically we've got the 6 calls in there, but I'm assuming that the shader compiler eliminated 5 of them because they weren't used for anything. Normally the shader compiler is pretty aggressive, right? It's not going to leave dead code in there for obvious reasons. They're trying to be as high performance as possible, so they're not going to sit around sampling textures that nobody then uses. So we can start to get some performance profiling information today. We also probably want to figure out how much time we are taking and figure out how we're going to get these voxels down quickly, a bunch of stuff like that. So we got a lot of interesting work to do, but hopefully we won't hit too many more GPU snags or anything like that, so we can mostly have fun with the lighting and try to get it into a position where it's working. Like I said, the main thing we need to do now is try to figure out to what extent all of these voxels can be sampled together. That's obviously something that we can kind of start to layer in a little bit. So since I'm pretty sure that these voxels will get sampled the same way, we probably don't need to worry too much about that part, but what I do not know is to what extent the voxels are getting sent down properly as separate voxels. So what I'd like to start by doing just really quickly to get us back into the swing of things today is I'd like to go ahead. You can see if we go to the Z-bias program here, so let me just jump to that. You can see where we're doing our sampling. Here is the sum total of the lighting sampling that we're actually doing. This is the part we're worried about. We don't know how long this will take. It's a requirement to sample 6 voxels. Now, what we can do in the future is we can probably keep this to 3 voxels total, maybe by being a little bit creative. I'm not sure how hard that will actually be, but it might be kind of difficult. We'll see, because I don't know to what extent we can use indexed lookups into samplers. It may be that we can, it may be that we can't. And again, that's really about how the shading language allows you to reference things. So worst case scenario, we have to sample 6. And in the case where we have to sample 6, that would be our least performant case. And like I said, just don't know how bad that's going to be. And so one of the things that we can start to do, again, to look at the frame rate cost, one thing I did is I opened up Nsight. I asked it to take some frame profiling for us. Couple of things I don't know. I don't know how much time of that is spent in some of our lighting stuff that we haven't really worked on yet. One thing I can do there is if we go look at when we're calling compute light propagation, that sort of stuff, are we doing anything in end lighting computation that's actually expensive, or that we can get rid of? So for example, we're calling compute light propagation. Let's say I got rid of that. Let's say maybe I got rid of all of this stuff, right? So we're not really doing any work in the lighting computation. Again, I'm just trying to keep it to just the voxel work so that I could get just a basic idea how fast that is. And so here is that same code running with that stuff commented out. Again, don't know how fast this is. So what I'd like to do is, again, run it under Nsight, just get some ideas of how is that working, right? So let's go ahead and do that. I'm going to load up Nsight here, and then I'm going to launch the frame profiler. And that should just give me an idea of how slow things are, right? Now what you can see on here is it's saying that there's a 22 millisecond per frame hit, right? And of course the problem is I really just don't know where that 25 milliseconds is getting spent. I don't know. Yeah. I don't know if I capture for live analysis. We don't know how accurate this actually is. But what you can see here, if you believe this diagram, which I don't know if we do, right? But let's suppose we did. You can see here that it claims we're only spending 4.66 milliseconds on the graphics. And if you look at what is detailed here in the texture calls, you can see where the various calls are happening, bind texture calls, the vertex array calls, these sorts of things. Use program, bind buffer, right? Here's the texture submission. You can see that we're spending 2.52 milliseconds and 15.13 milliseconds. In fact, and you know what? That right there looks like the time, right? So if we look here, you can see we've got this sort of 4.66 milliseconds. It looks like that is talking about the GPU time. If we believe this performance analysis, that right there is our problem. So this submission of the 3D voxel down to the card, really, really bad. That's a huge problem. And if we just look at our frame time, that's pretty much where the problem lies. That's actually surprisingly good news. It's good news for two reasons. One is we can reduce the size of the voxel, which will dramatically reduce the cost of submitting it. We can probably cut that number in a quarter by just changing to a 64 cubed voxel instead of a 128 cubed voxel. So that's really good news right there. The other good news is we have done literally nothing right now to make sure that the graphics card is getting that voxel in the most expedient way. And what I mean by that is we are literally just taking a user space pointer and we are saying to the graphics card, hey graphics card, why don't you take this user space pointer and do something with it, right? So that's the least efficient way for the CPU to do anything. It can't be multi-threaded because it doesn't know when we will touch that memory again. So it has to do everything behind the gltext subimage call right away. It has to do a full copy into its own space to make sure that it preserves the memory that's there at the time of the call. And furthermore, it has to do at least that one copy, because even if it didn't have to do it right away, it can't, and it could overlap it, it still has to do it. And the reason is because we didn't allocate the memory for that transfer buffer from the graphics card, so it can't put it in a space where the graphics card itself could gather it and do swizzling on its own or whatever it's going to do. So we're feeding it in the worst possible way is probably the best way to think about that. So the first question would be, well, you know, can we just like can we optimize this out somehow, that gltext subimage? Let's just verify to ourselves, because I don't know. If we terminate the running program here and we go back to our code, if we, inside the OpenGL renderer itself, no, yes. So if we go to the renderer itself, and we just go down and look at how we're doing things, every frame we send down this, and that's what we're going to need to do, because we need, when we send it down, when we send down the lighting information, every time we need to make sure we... Wait. What the hey? Why are we doing this every frame? I don't know why we're calling gltext parameter I so many times here. That's not what I intended. So that's a little weird. Hold on a second. Sorry, this is not what I wanted to talk about right now. But OpenGL init. When we create these textures should be the only time that we actually need to do that. So that was a mistake. Those should have been here, right? So sorry, let me just make sure that that's fixed. That we don't need to be... I don't think that would have done anything because the OpenGL layer does a lot of diffing, so it probably just ignored those anyway, but I just want to make sure that we move those to the right place. Yeah, because those did not need to be called there, and that's just getting cruft in the way, and no point in that. All right, So this is the call that we're talking about here that takes a while. If I just actually throw in a local persist here, that's just like only twice or something, I don't know. And we just send this down or for the first 10 frames or something like that, just to make sure that the game has actually sent some information down to it at some point. What I can do is just say like if only twice, and of course now it's 10 times, so that doesn't really make any sense. What I can do here is just say like, oh, all right, let's do like only twice. This is probably fine. Leave that there. Let's only do this a few times. Send it down only a few times, right? And this way we can get a feel for the speed if we're not doing that texture transfer, right? So just keeping that texture transfer out of the loop. So here's that, and we're running now. Off we go. If we double check the speed now, so I'm going to launch it from here, and we look at what the profile is, my assumption is the profile will jump up dramatically. And you can see it here. Now we're at a very reasonable frame rate, right? That's actually hitting 120, which is pretty good. And as we get out to a harder sort of view, we're still way above 60, right? And so if our goal is to ship this game on a modern graphics card, it should run at 60 frames a second. We're well within tolerance here, and we haven't really done much optimization work. So that's good, right? That's a good thing. Now, let's continue down this path a little bit just as we go here. Let's try and... I'm going to go ahead and hit terminate there. Or try to. Nsight isn't great about closing apps, in case you're wondering. Like, it's like, hello, could you terminate my application, please? Yeah, I don't know. Who knows? Anyway, point being, if we push on this a little bit more, what I'd like to do is, when we go and submit our voxels, let's put different things in different voxels. So, for example, if I go into the Handmade lighting code, and you can see us stuffing our voxels with our structured art here. Again, structured art, a very important way to debug things and test things. Because if we just put real artwork or real lighting in here, it's very hard to tell if it's wrong subtly, if subtle wrongs. Obvious, like serious bugs show up clearly, subtle bugs don't. So structured art's a really good way to do that. Plus, when things are in serious bugs, even though the real artwork, you can still tell there's a serious bug, you can't necessarily see what the serious bug is. But structured art makes it much easier to see. If you only see the red channel, for example, you know that it's this particular voxel is being overrepresented and the others aren't or something, right? You can see through the structured art clues that you wouldn't see to the bug, even if the bug would have been clear in normal circumstance. So structured art, very important. Putting debug values into precise locations in your artwork is very important. You see me do it many, many, many times. It's one of the most important tips. I credit Mike Biddlecombe for that. He's the one who even coined that term for me. He probably didn't coin the term in toto, but he was the one who introduced me to that term, and I was like, structured art, yes, very smart. And so what we want to do here is start to take a look at, we've got these box indexes here. What if I start stuffing the other box indexes with something else? So here I'm going to say, all right, let's do all of our box surfaces here. So when we talk about our boxes here in the order we normally put them, south, north, down, up. And my goal here is just going to be, let's fill these voxels with something that lets us know they're actually working. And at the same time, that will force us to know that they're all getting sampled so we can get a realistic profile estimate of how much that fragment shader is going to cost us in the worst possible case. Unoptimized, just running itself into the ground. What's that going to look like, right? So what I want to do here is I want to create sort of a set of lightings here that are going to be structured arts that's structured in such a way as to put different things into the colors of each voxel. And so what I'm going to do is duplicate the code I had up here, but change the striping patterns, right? So basically, like, I'm going to compute different patterns for west, east, south, north, down, and up. So what I want to do, we'll start out pretty simply. What I'll do here is say, let's go ahead and stripe further apart so I can get kind of two different stripe patterns going. And so maybe what we do here is we say like, okay, let's suppose that we do like a x divide 2 kind of thing. So now what we're going to do is reduce that period down, right? And so like if I do something like this, right? And then I'm going to do something like put them into different ones. So we'll do west and east stripes like that. In fact, maybe we'll just do those two for right now. And so now if I run, what I should see is I'll only see red striping because we're only drawing the westward voxel. And so I'll only see the red striping, and again, it's twice as banded as before. Before the bands were more frequent, now they're less frequent, right? And the other thing you can kind of see here too is I think our voxel's just it's too dense, right? Just even looking at it, it's just too dense. When you look at how it lies onto these things, I think we probably have just way too more density than we need to capture the kinds of lighting details that we're trying to capture with the voxel. So in my opinion, this is also probably too big, and so we can reduce that size down. But I don't want to do that yet, like one thing at a time. So now let's go into the fragment shader and let's try to pull in some of those other channels. Now we know we're already asking for them, but like I said, they're getting optimized out. So if we look at where this light sampler east and west, they are getting pulled in, right? But you can see here we just take the light west RGB, and that's not going to cut it because that means that it can just optimize out the light east entirely. So if we were to do something where we sum these, in fact, you know what? I should probably do this a different way. Let's do it like this. Let's take the light data and let's just set that equal to 0. And then let's just sum these in a way that's just convenient for us for debugging purposes, right? So we'll start summing in the light unpacks for each of these in series, like so. And so I'm going to go ahead and compile that. And now I would expect to see two different sets of bands. One set coming from the westward-facing voxel, one from the eastward-facing voxel. That's the hope. Looks like I screwed something up. What did I screw up? That is what I screwed up. Probably should have shown you a new feature. Actually, if we have an error in our shader compiler, again, I'll do it. In fact, let me just do it for you. Suppose I didn't know that, right? So one of the things, George X13 Pixels on the chat recently updated our debugger, Remedy, debugger of champions. And if you look here, like before, oops, if I spell it right. Wait, why did that compile? That was supposed to crash. Well, not crash. It was supposed to assert on the shader compiler, right? Did I miss it? Yeah, there it goes. So if you look at something like this, right, in the past, when you were trying to view strings, it was hard in here because it had, some different displays for them or whatever. In theory now, supposedly we can just do this. And if you do comma stir on something, then you get like a little effectively text editor view in here. So you can see really cleanly like what the actual contents of the string is. It's really nice. It's much nicer than the MSVC one, which pops up like a modal window you can't get rid of. So this is kind of nice. You can just kind of look at this in here, and you even have a scroll bar. So if this happens to be tiny and you don't want to expand it, you can still see the entire string conveniently in there, formatted properly, which is really baller. And just want to thank George for doing that for us. Again, it's so nice to have somebody who knows what they're doing working on the debugger instead of the Visual Studio debugger, which no one who knows what they're doing ever works on, as far as I can tell. So it just keeps getting worse, whereas this one keeps getting better. And so thanks for that. That's really good, and it will help us out a lot. So that's pretty awesome. Anyway, just wanted to mention that was there. We didn't need it this time, but we're definitely going to need it sometimes because as we oftentimes will put mistakes into our shaders. So anyway, going back to the correct version of the shader in theory, if we take a look here at what we've got, you can see now we're pulling from both voxels, right? Because one of them is the green stripes, one of them is the red stripes. So what I can do now is start to layer some lights on top of this, and that's what I'm going to try and do. So the south and north voxels, what I'm going to do is actually go ahead and make those be a higher frequency stripe on top. So I'm going to go down to just the, again, looking at the frequency here. Instead of it being half the frequency, I'm going to use the full frequency. And the south and north voxels, south and north voxels, they will just be effectively the same striping, but on top at a higher frequency, right? And so if we go ahead and do that, and you know what, maybe not. Let me do that instead. So every fourth one, they will kick in. That might be easier to verify, right? So every fourth, we should see a red and a green highlight on that. Let's go ahead and kick those in here now. And well, for good measure, let's go ahead and kick these in here, because we know we're going to need them. So now we're sampling from all the voxels, and you know, maybe we can just go in here and do something like this. So now we've got everybody, and we can just stuff the down and up. So now we've got a Z stripe in there too. And so now we should be able to do some kind of light verification, hopefully. We'll find out. Whether or not we can actually pull from all these voxels successfully without maybe if there's any kind of bugs in how we were sending them down or anything. But, you know, this is in theory sampling all the voxels and just trying to verify which ones are in there at this point. So looking at it, yeah, so the green striping, I don't think that's doing exactly what I had hoped. Hold on a second. Let's do it slightly differently. Let's do it this way. I think this will be easier. So this will basically say, look, we should see 2, 4, 2, 4, like on the stripes, we should just see like regular patterns now. And looking at it, that looks a little still more frequent than I would have expected. X mod 4 equals 0, X mod 4 equals 2. Am I just doing something stupid here? I might be. If I said X mod 8, I might be doing something stupid here. But basically all I was trying to do is just say, look, let's space out these things fairly far. But I guess I didn't. There we go. That's a little easier to see, right? So our voxel is just way too dense, it seems like. But anyway, now you can see we're getting a certain spacing there. If I turn off the mod 4 people, so let's go ahead and move the mod 4 people down here, like so, right? So if I go ahead and turn off the mod 4 people like this, then what we should see, and in fact I can toggle this at runtime actually if we just run it so we can see it change. If we run it, we should see fairly far spacing for our different ones, and you do, right? So there's our, you know, fairly distantly spaced. Now I turn on the second set of lines, we should see all of them become more frequent, right? Hopefully. Oh, but we won't because we're not sending it down every frame. So let me run it again, because remember we stop. And now we should see more frequent on each, and we do. So I think we're pulling from all of the voxels now. And since we're pulling from all of the voxels now, I think now I can go in and actually run the frame profiler and see what's up, right? So here's our frame profile. Here's us pulling from every voxel, right? And we're a little high on there. Let's go ahead and do a capture for live analysis and see who's taking the time. We'll just see what's up with that. And looking here, honestly, it looks like it's just chewing through this like, you know, it was steak tartare or something. It seems like really the GPU just eats it for breakfast. So it's just us. It's just our CPU side stuff. So in theory, if I nerfed this, our frame rate would presumably go up. So let's actually try that. See, I don't know if Nsight can actually do the reload properly, so I don't know if you can hot code reload inside Nsight. That may be asking a little bit too much, but I'll try it. So here's its frame rate estimation, right? And I'm going to go over to the code. I'm going to take out the part where we actually fill the lighting buffers because they've already been sent down, so it doesn't matter. And we're going to see on the reload what happens. Yeah, there it is. So what you can see is actually the GPU just crushes this. So it, you know, because this is a 1080, I think, in this machine, or a 980, 1080, 980. Maybe it's a 980. You know, I don't know what's in this machine. I don't remember. I don't remember what's in this machine. That's how bad it is. My work machine has a 1080 in it, but this machine is older, so you know this might not have a 1080 in it. Anyway, the GPU eats it for breakfast. If I actually go, take a look at what's in this machine here. Hold on a second. Can you terminate? Disconnect. There we go. Close. Do something for the love of God here, Nsight. Thank you. So yeah, if we actually go look at what we're running here, I don't actually remember. Does this actually tell us? It doesn't tell us. Thanks Windows. We'll take a look at the NVIDIA control panel. If we go look in here at the system information, that should tell us which graphics card we're actually running. And it is a 1080. Yeah, there we go. I'm like, I thought it was something good. So anyway, this is a 1080. It's obviously not the latest and greatest. The latest and greatest is like one of those RTX cards to 2080, or I don't even know what the heck they're called. The numbering schemes are complete marketing FUD and make no sense. But point being, it's still a very fast graphics card, very capable. And so I suppose it's not surprising to see that nowadays these things are so powerful that pulling from 6 voxels at a time is like not even really interesting to them. They're just like, yeah, sure, whatever, man. Here you go. I don't care. So it looks like this is totally fine. And not only does it look totally fine, but it looks like if we wanted to, we could increase the number of voxel samples we're taking. So we could probably even go more nuts with it if we wanted to. So what it looks like to me is our biggest problem is how the heck do we fill these voxels with something, right? That looks like it's going to be our biggest challenge. And the reason that I think that's, that it's a big challenge is because, again, I really don't know that we want to put voxelization on the GPU side, because that would require us to use unordered access views, and that's just getting into the territory of like only really good graphics drivers probably work at all for this, and good graphics cards, because unordered access views are a whole nother ball game. We've never really covered them on Handmade Hero, but basically what you have to remember is the graphics pipeline is set up so that fragment shaders get invoked on blocks of pixels, probably like 4x4 or 8x8 or 8x4, blocks of pixels, at least 16 pixels at a time. Could be as much as 32, 64, who knows, right? But they're getting it invoked on blocks of pixels that are based on the width of the ALU units in the graphics card. So if they've got AL units that do 16 multiplies at a time, then you're going to be a 4x4 block of pixels or something, right? Because you're going to do them all together. And when you do those blocks are effectively like, you have to think of those blocks as being almost like bins that are getting fed into a backend that has to serialize the work to combine them. And the reason for that is because graphics has a draw order, which is kind of annoying, but that's just how graphics works. If I draw one triangle and I draw another triangle, and the second triangle overlaps the first triangle, the second triangle is the one you're going to see, not the first, right? And so if there's a Z buffer in there, the Z buffer will do testing or whatever. But if you just have Z buffering turned off, the second triangle is the one that draws, period, right? So that whatever draws last, it draws. And the graphics card is not allowed to pick an arbitrary order. It has to do the same order every time. So even if it decided that instead, some other triangle should draw, whatever, it has to be the same every time, or you get flickering, right? And so what happens is there's a part of the graphics pipeline that takes all of the filled pixel chunks and combines them together to produce the final output chunk for that region of the screen. If lots of triangles overlap it, they have to get reconciled by a blend unit. And if you're wondering why like blending is really weak, why you have to specify like a fixed equation with some fixed coefficients, and that's how blending works, rather than being able to write your own blending shader, that's why. It's specifically because that part of the back end has to be super fast and it can't really be wide because it's serial, right? It has to go in order. And so that's why you don't see programmable blending very often on very many cards, is because really high throughput cards can't afford it, right? So, all that said, so unordered access views are saying, forget that. We just want to write wherever the heck we want to write. We want to do whatever we want to do, right? And so an unordered access view is basically saying, I'm not going to tell you what block of pixels I'm even going to touch. It could be any set of pixels. Anywhere in a texture, I don't care. And you're going to have to deal with it. So it's basically like saying I get to write anywhere in the frame buffer I want to, right? And so an unordered access view is just really bad in that sense. It creates, on the graphics card side, a need to basically treat the blending output unit as almost like a cache rather than an actual guaranteed part of the pipeline, because now you have no idea which set of blocks I'm even talking about until after you run the shader, right? And so obviously graphics card companies are smart. They know what they're doing. They've probably on the high end, like I'm sure on this GPU right here, I'm sure their unordered access views probably run almost as fast as not, right? I'm sure they probably got the chip organized so that it caches it properly and just pulls in the right blocks, and whichever ones you touch get synchronized through a back-end thing. I'm sure they've got it dialed, right? Fire up Intel integrated graphics someday, and I'm not sure if that's going to be the case, folks, right? And so I'm nervous about using unordered access views because I don't know. I'd have to ask a person who does more GPU compat work. I don't really know how likely unordered access views are to work in a lot of places and work fast, So I'm really nervous about voxelizing things on the GPU side is scary to me. And so that's a problem for us because it means that if we were to voxelize on the CPU side, it kind of makes it tough. CPU side voxelation may be kind of rough, but we can use 6 thread. We can probably count on at least 4 threads, and we can do it wide. So we can do 4 threads and 4 wide, which might get us a ballpark a 16x boost. So it's possible that it could work. we could, in theory, do a good job voxelizing on the CPU side. So for now, I'm going to hope that we can. And then we'll deal with the can't part of the maybe not, maybe we can't part when it turns out that we can't. Because, hey, we would want a reference implementation running on the CPU side anyway, so we can get it all working there first. That's where we're at. All right, so let's start by actually looking at how big this voxel needs to be. So here is the size of a voxel stripe. I'm going to go into the OpenGL renderer temporarily. I've already turned off MIP mapping. I'm going to turn off linear blending as well. The reason I'm going to turn off the linear blending is because I don't want it to blur the boundaries. I want to see exactly where these voxels actually are. And so when we create in OpenGL init, when we create these, I'm going to turn off this filtering right here so we can see where the voxel boundaries themselves actually are, right? And so if I run it now, in theory, what I should see, maybe, if I did it right, is the width of an actual voxel, right? So if you take a look at how detailed this is, let's move out to an area where we're fairly zoomed out. So I think like the most zoom that we ever get, and it may even be too much zoom, I don't know, but it's something like this. If you look at that amount of lighting, you know, I think that's probably fine. We need it to be a little bit bigger than that. So the light bounds need to be spread out a little bit more than that. I'm not sure what's going on there. Let me take a look at that. So in here, we're looking at this world camera rect. I'm guessing that's just wrong or something. I actually don't, that number is actually what's wrong. Why did we do that? Don't we know that number? Like, what the heck? I guess we must just not be saving that number. You know what I'm saying? If you come in here, you can see us doing this rotation, and we do like delta stuff here and blah, 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 right? I'm going to go ahead and just guess that the simulation center versus the, like, it should probably be a delta from the simulation center. I'm guessing. Don't really know. But I think that's probably the case. So in here, if I like took a look at this, if I took the camera z-axis and did an inner product on that, you know what I'm saying? If I did something like the simulation center, so the location of the camera, right? Like where the camera actually is, versus the simulation center. In fact, let me take a look here. So we've got, in this, we've got the game camera, and you can see here we've got sort of the stuff going on here. You can see right here the focus min z and maxi. I think that's what we want, right? So I don't even have to do this computation I was about to contemplate, because this is the value we actually need. So I think the expected focus min z and the expected focus maxi is like the region in which we're supposed to be looking. So I think if we just said like the bounds between those, I don't know exactly how far through those we want to go, but let's go ahead and say yeah, I'm gonna sort of ballpark it here. Let's go ahead and say that if we took a look at the world mode camera.expected focus min z, and we want to sort of bound that region, maybe we do sort of a split. I don't know. So something like this. maybe what we really should be doing is taking both and then sort of building a bound or something. But I'm not sure. But let's say we do something like this. I'm just going to play with this a little bit and see if we can get those bounds a little bit better, because the bounds are kind of crappy at the moment, and I'm not sure why. There might be some bugs in it as well. So now one of the nice things is you can kind of see we don't really have that lighting problem anymore. We're actually actively lighting sort of the correct region more so than we were before, right? We may be lighting a little larger than we should, so we might want to we might not want it quite that big. It's hard to say, but if you take a look at the sort of the difference between these two. Yeah, hard to say. But anyway, I think that's fine for the most part with where the light is. I think that's all good. So let's leave it like that temporarily. And so if we take a look at how sparse that voxel is, I mean how detailed that voxel is, even in this case, it's just way more voxel information than we need. It's almost 4 per grid cell. We only really need 1 per grid cell, right? For Nyquist, we could go to 2 per grid cell, but I mean it's just not. I don't really think it's necessary. So if you look at even for a pulled out version, it's just way more detail than we need. So I'm going to say we can definitely drop it down to 64 at the very least. We might even be able to go lower than that, but you know I'm going to say that at a minimum we go to 64. Oops, because 128 is way too detailed, and we're just going to be blowing a ton of time voxelizing stuff because it's way more detailed than we need, and I just don't think it's worth it, right? So there's a much more reasonable size for the lighting, but again, it seems like it's probably, I wonder if 32 by 32 would actually be better. It's still just a little too detailed, I think, right? So I kind of feel like maybe what we want is more like 32 by 32, and we could try to get the lighting bands a little tighter in general. And so now you can see it's a little, I think it's a little nicer, right? Now you can kind of see that it's roughly, yeah, it seems like roughly the right size. I do think this band, the band in Y is too, it's too thick, and I'm not really sure why that would be the case, because the band in that direction should actually have been smaller. So I that doesn't quite add up to me. I think there's some kind of bug in our algorithm or something. Because riddle me this. If the bounds are shorter in Y than in X, which they obviously are, you can see that they are, right? I mean, it would help if I could move it back a little bit so we could see the top bound as well. I guess it's kind of hard to see the top bound, but I mean, I only see 1 stripe on there, right? That doesn't really make any sense. So something's wrong with our sampling or our fill, but I don't, or our constant that we sent down. So something weird is going on, and we need to fix that. So let's figure out what's up with that. So in set light bounds, like if we have in light dim here, and we do this to map into the voxel space, I'm wondering, is that computation like bogus or something, or did something weird happen? So I kind of want to know what that, like, what is this process doing? Is something untoward happening there? I'm going to go ahead and see if I can look at operator divide on the vector. I just want to see like what that will do. So here's that that code. It looks like it should do 1 over each of the dimensions, which is what I wanted. So I'm not sure what's wrong there. Let me look at the shader as well, and then we'll just step through it and try to debug what's going on, because something weird is happening, and I'm not sure what. So if we look at the Z-bias program, which is right here, here's how we're producing this. We first subtract the voxel min corner away. That should put it relative to the min corner. Then we multiply by, well, we effectively divide by the total length of the voxel. That should be giving us a 0 to 1 on each of our dimensions. So again, not really sure I see why we're getting a problem there. If I pop back to lighting really quick just to see if there's anything weird happening here, I don't see anything strange there, but you know, did I mess up the indexing? So this is our x coordinate, right? For every y, we need to move the full voxel dimension, right, which is this, forward. We could go double check that that's correct as well, I suppose. And then for z, we need to move that squared, right, because it's an entire y sheet of the voxel at that point, xy sheet. So I don't know, like, but something's up. So we need to debug that first and make sure that, because we should see each of the voxel's the same in every direction. It's 32 by 32 by 32 now. So we should see exactly 4 stripes in the lighting, and in each one, that's what we needed to see, right? But you can see when I open it up here, that's totally not what I get. And interestingly enough, you can see, like just to underscore just how wrong this is, what you can see happening is, if I go back here and you say, if I wanted to know how many times you can go from 0 to 8 inside 32, right, I would expect the answer to be 4, right? So x mod 8 at 0 will be 0. I then have to go all the way up to 8 before it's again. So it happens at 0, happens at 8, it'll happen again at 16, and at 24, and then there is no 32 because that's when this loop would stop. So that's 4 stripes of red, right? Oh, but this is if zeroed in. Okay, never mind. That would explain that. So now, do I see 4 stripes of red? Let's find out. So I would expect to see 4 stripes of red, and along X, it looks like maybe I would, right? 1, 2, 3, 4. Yeah? So that's good, right? That's exactly what I want to see. So now the question is, why don't I see any of the green, right? Where's the green? And, you know, I don't know if I was to look at this, the light east value, right? It should be coming in here. It looks like that's getting set. If I go to the shader, here's the sampling. It's being sampled by the same exact parameter, right? So I don't know. Let's do some testing. Let's suppose that I look at the light east value here, and I say, what if I change it to light west? So now it's in the same voxel, right? So those stripes are not on 2 different voxels. Oops. They're now on the same voxel. So it's not the sampling of the voxel, right? In terms of which one we're sampling. It's either the sampling of all the voxels, period, or it's the filling out of all the voxels. But it has nothing to do with whether it's in the west or the east facing voxel, right? So let's think about that for a second. we know that we get this problem in either case. That means that, I guess, maybe the way we're sending down the total dim is wrong, because the min corner looks like it's in the right place, but the total dim, the Y total dim, must be wrong. I mean, just looking at this equation, right? First of all, this is busted. That was supposed to be an X, so that's great. I don't think that's enough to mess with it much. I also don't understand why... Oh, wait, no, that's not what that was supposed to be. That's shifting the Y by 2. Never mind. So that's fine. But again, we probably want to fix it. You shouldn't have to do that because that should have been accounted for in the camera rectangle stuff. You can see us adding to it here, but we're adding to it on both counts. Let's get rid of this for a second and see what we've got. So I think we probably want to work on our query anyway. So I think we're going to maybe leave it like this and then just fix the query rather than having those weird, like, you know, adjustments in here. So I'm going to leave this out for now. And we will take a look at that in a little bit. The add radius 2 part may need to stay, but we'll see. So anyway, because we do kind of probably want an apron, because we need to get light that comes from the outside, so I guess we'll see. But anyway, when we've got our set light bounds here, I want to know what's going on, why we don't see those stripes. So I want to know what's going on with this inv-light dim here. So I want to kind of look and see what this value is and just why we're getting such a strange disparity between the two. And maybe there's something else going on there as well. So I should check here. As well, when we look in, you can see just to make sure that this is, you know, getting sent down right. It looks like it is when we do the push setup here. And I could also look to see where we actually get those out. So where we actually send them down to the graphics card, that's going to be in the use program call for ZBias program. So in here where we have this use program begin, we're sending down the min corner and the in total dim like this. It looks like it's right. I mean, for the most part, I don't see anything particularly odd happening there, so it feels like it's probably okay. And let me go ahead and switch our build mode now to not be optimized. So this will be a -OD. And I'm going to go in and inspect those variables because I don't really know what's going on. I'm not sure why I'm getting that kind of unexpected pattern there. So looking at the game in debug mode here, again, so just to recap, I'm seeing the red stripes I expect. I'm not seeing the green stripes that I expect to see. And for all I know, it's because the Y dimension is like really large or something, like just totally wrong. I don't know. And so what I need to do is just figure out what's going on there. So I'm going to look into the world mode here. And I just want to try and figure out, like, all right, if I look at the world mode, where it's actually getting that inv-light dim there, like, I want to break right here. And I just want to see what we're actually sending down. So if we look at inv-light dim, you know, you can kind of see here that it's... The Y is twice what the X and Z are. You know what I mean? So, that does imply we would expect to see half like the distance between the stripes would be 2x off, right? But I'm not sure that's enough to account for it because if we look in here and we say, well, all right, if it's 2x off, that means that let's say it's even off 2x in the wrong direction, right? Then what we would expect to see is, well, it would mean the first green stripe would be about there, right? It'd be that far, because it'd be the second one. So it'd be like there, right? And ain't no green stripe, my friend. Ain't no green stripe. You know what I'm saying? So something weird is going on there, and I don't know what. I really couldn't tell you. And so I'm going to look at a couple different things. First, I'm going to go validate the... I'm going to try and validate the actual voxel, because I don't know if that's right. So if I am in the OpenGL code, right, let's go down to where we submit it, like here. And let's just set a breakpoint on the submission line and look at what we're actually sending it, because, maybe that's totally wrong. Who knows? So if we go here and we take a look at the light data, and we're trying to send down, a 32 by 32 by 32. So, maybe there's an unpack weirdness going on here or something. But let me also change this to hexadecimal. I think you do comma X for that already. Yeah. So what you can see here is there's the red stripes every 8, which is exactly what we would expect, right? And if we keep going, what we should see eventually is we should see some green in here, right? But we don't. I don't know what that means. Not sure what TBI means there. But we don't, so what I'm curious about is, well, okay, so honestly there's, something that's kind of confusing here. Oh, you know what? No. The stripes are in here. What am I talking about? I'm like, the first one should have had it. These are the stripes. So there's our first green stripe, which we saw, right? So that's good. And what we should see is then after we go 8 more counts of 32, we should see another band, right? Which we may run out of space here for. I'm not sure if there's a way in Remedy to tell it to do more. Probably like you put it after this or something. But I don't know that I really want that anyway, because what I would rather do, I think in this case, is I'd probably rather use an offset so I know where I'm at without scrolling down. So if we were to look at where we expect the offset to be, right, we would expect, remember each stripe is 32 long. So we would expect the next one to occur around 256, which we can jump directly to. Right, so let's just start at, I don't know if I can do this. Can I do that? Yeah. So we'd expect the next one to be here. It's not here, which isn't great, right? So I'm not sure what to make of that exactly. If I was to ask Remedy to display more of these, let's say 512 of them, then what I should see is, the 507 is the marked one. The 4354 isn't. So when I get up to 256, yeah, it's just not there. So maybe I just don't know what I'm doing and should retire from programming. That seems like a likely thing to expect. This code is obviously incorrect, and I just did it wrong. Right, I don't know what I'm doing. So if we take a look at what we would expect to have happen here, right? So let's suppose we take just the first z layer where z equals 0. Then I expect this to just be 0. And then I would expect the x to be an offset and the y to be strided by 32, because voxdim is supposed to be 32, right? That's what I'm expecting, because that's the way I expect it. Now, we should maybe check that it is, but, I mean, we know that the x is striping by 32 correctly. At least it seems like it is. You know what I'm saying to you? So I'm not sure what's up with that. So anyway, what I would expect here is that at y equals 0, I should hit this case, which is y mod a equals 0. And then I would expect once and that would set light east, right? And then the light east code would just go in here. Pretty straightforward, right? And then I would expect, furthermore, to see like the, yeah. I would expect to see it happen every 8 times 32. Now, I'm going to hazard a guess and say maybe what happened is I've got the pointers messed up. So maybe what happens is this light index voxel bracket stuff is not working properly. Do you know what I'm saying? So for example, if I go to commands, let me take a look at where that is. In here. How is it set? And so if I look here, I've got pointers to 6 different banks of U32s, right? So the question is, how do I initialize those? Maybe I initialized them wrong. There's a pretty easy way to test. I can just set these at different values, but I also just want to look first and see if I set them wrong, because I may well have, right? So actually, if I just go to OpenGL init here, and I go through and try to find out what's going on with the initialization of those parameters, oh, you know what? It's begin frame, actually, isn't it? Yeah. So here is the place where we set these up, and we set the 5 pointers up here to be OpenGL light data. So if I look at what the actual OpenGL struct has in it for the storage here, just trying to make sure it has. Oh, great. So that's totally wrong. I don't know what OpenGL light index voxel dim is, but it's something that has nothing to do with what we defined. So that was good. Fantastic. What is that doing there? I don't know what any of this stuff is. That's old stuff. Great. We just had a typo. Fantastic. Where else is that being used? Yeah, none of this stuff is good. That's all bad. That should be in here, right? So we actually want to use this stuff. But that was our problem. So I kind of knew that right away once I inspected the voxel, so that was pretty easy to figure out. That's good. But like, yeah, I don't know why any of this stuff was being set there. It should be in here. Like, we obviously just got confused, probably because I only program this once a week. But anyway, so you can tell that that was just being stupid. So we want these in the renderer, and we want them to be specified here. Max light probe count, right, should just be something that we define. And we don't really know exactly what that is, but it's probably just something like this, or and then for light occluders, same thing. And it's especially stupid that those are OpenGL because we don't actually use them on the graphics card. But what are you going to do? OpenGL max occluder count. That's this. All right, try this again. So now let's see what our stripes look like, so we know what we're debugging here. That is much closer to what I would have expected to see. And I want to do something now, because we have clamp to edge set, I want to go ahead and do, when we fill out our voxel here, just so I can see where the edges are, what I'd like to do is set the edges as well. So what I would like to do is, like, if we're on an edge, set that like very clearly. So for example, I'll do like if z equals vox dim minus 1, you know, light west or equals that or something. And we can just set these up so we can see where the end is. And that'll just give us some ability to see what the actual bounds of the lighting is on the screen, which we kind of want to be able to do, right? So if we look now at where the actual light bound is, you can see like very clearly that there's 4 stripes across and 4 stripes that way. We don't really have the ability to verify the depth of this voxel very well, because we don't really have any good places to look at striping vertically. We need some kind of like a tall polygon or something, right, to get some information about that. But we can sort of go here and hop onto an area that at least has some stuff stacked on top of each other, move the lighting so it's kind of over it, and then we can probably see something about that, maybe. I mean, I don't really know. But here, if we look, you can see the blue stripe, right? And so that would be a size of a voxel in Z, which is totally fine. And so, yeah, like looking at how big these voxels are, that just seems probably fine. And the only question I have is, if we expand the light bounds out to actually fit the area properly, what does it look like? Right? So, yeah, you know, maybe 32 is a little bit too much. I guess what I would say is depth-wise, it's definitely not too much. So we may want to use irregular bounds, like non-uniform bounds. We may want to do like 64 by 64 by 32, or maybe even 64 by 64 by 16. I don't know, depending on how deep we want to go. But just the stacking is probably not so high that we would have to actually have the same resolution. Like a 64 by 64 by 32 would probably be fine. We wouldn't need a 64 by 64 by 64, probably, right? And so what I would like to do is maybe go a little bit further with this and try to make it now so that these are like that we have a stable voxel grid, and get that working kind of on top of what we've already got, or something like that. Not sure yet. It's a little bit hard to say. Maybe let's just do the lighting first. Maybe let's just get that working first, and then we'll worry about fitting this thing on there nicely. That's probably fine too. So if we run now, excuse me, if we run the game and we just look at what comes up, that's like totally fine. It's pretty clear that the resolution is like way better than we even would need it to be. That's especially true in Y, but I think that's partially because it's kind of sized a little inappropriately at this point. So assuming we want those to be kind of regular, what I might suggest is saying, look, when we do the light bounding, maybe we make sure that the Y is actually the same as the X. And so, you know, in here we would say something like, for the light bounds, let's take the min Y and subtract like an adjustment and in both, and just say, look, we want the adjustment to be applied to Y such that the dimension of Y is going to be the same as the dimension in X. So it's it's a proper cube, right? So if we did that, we would say something along the lines of adjustment Y equals getDim light bounds x minus getDim light bounds y. And that just lets us, compare those two and make sure that the y is the same. So this would keep our stripes the same size, which I think we kind of want, because we really don't want the lighting to be anisotropic in terms of how it's sampled. We would like it to be nice squares. And so here you can see what happens when we make it into a square. And yeah, that doesn't fit the screen region maybe as well, but I'm not that worried about that, right? Okay, so if we start doing lighting on this grid, and then we worry about locking it to the world as a separate pass we'll worry about later, this is clearly high resolution enough. It's arguably too high resolution, so we may actually size this up a bit from where it is probably. But we can get started now, right? So let's go ahead and start flooding these voxels. Also, if I look here, I would be interested to know if I actually turn on a grid now. So let's say I did something more like this. So I can really see the voxel very clearly. This is every other stripe will be a band. So this shows you the literal voxel now. There it is. And what you can see is inside a single cube, we have tons of resolution on that voxel. Like I said, arguably too much resolution. On the voxel, we probably want it even smaller than that, but it will get smaller than that once we get out to a large room. So if I come out here to a room that's very large, right? Like so. Now, in this room, which is kind of the most zoomed out the camera is, you can now see that if I go in and take a look at one of these squares, it's actually just at Nyquist, right? So it's 2 samples per square, which is probably fine. Now maybe that's still too small. Too fine, I should say. So I don't know. Maybe we need to even go up a little bit more. So maybe we should jack it up a little bit more. If I look at how we're running band-wise in Z, it's 3 as well. So maybe this needs to be a little bit smaller even still. I don't know. That would be great news because it's just less work we have to do. But if I was to drop it down to 16, I don't know. That seems way too low. And I don't know that we can do anything else. I think it has to be a power 2. So what we could do is use a 32 by 32 but not fill it all. But here's what that looks like, right? And that's way more like the resolution I actually want. When we hop out here, though, I'm assuming that'll just be too big. And so now if we look at how this lines up, you can see that it's roughly 1 voxel per light probe, which seems good, right? And yeah, I don't know. Maybe that's right. Maybe that's the size of the voxel we actually want. So I'm not sure, but that could be basically all we really need for the lighting resolution. I'm not sure, but that may be all we really need in terms of covering relatively good coverage for the kinds of scenes that we're looking for. That may be enough. So we'll start playing with it at that level, and we'll see. But I just don't know. I do think we may need 32, and the reason I say that is because if you look at what happens kind of in the outskirts of that area, what you see in sort of the outlying areas out here is if we were to actually scale this to fit the whole scene, it would have to be a little bit larger, and then you're starting to get down to 2. It'll actually encompass 2. So it's just really hard to say. But I do think 32 by 32 by 16 would probably be just fine. And we could just not use all the voxel. We could just only fill the center of it up and skip some of the outside ones if we find that it's too resolute, right? But I'm going to start with that for now, and we'll go from there. All right, so let's suppose we wanted to actually light with this thing and start playing around with that. What does that look like? Well, if I was to flood my voxel with something that would allow me to see that, right? Let's suppose that I sort of nuke some of this stuff for now. And what I'm going to do is I'm just going to take one of my voxels. So let's say the voxel for westward facing light. And I'm going to say that that just gets some light and nobody else does. So what I'm going to do is I'm going to send down some white light down that channel. And I'm going to see what happens if we lay in a lighting equation that's actually somewhat correct with westward facing lighting. So this is as if there's just a strong white light everywhere coming from the west side, right? And so if we have, if we imagine what this is supposed to say, we have a strong light coming from this side, bright white. Now, obviously right now, all we just get is a uniform light on the scene because we're not computing a lighting equation. So what we want to do now is go add a lighting equation and see what happens, right? So let's go to the Z-Bias program. And let's try to do an actual full-on lighting equation, right? That we can drop in here and have some understanding of what it's actually doing. So here's where we get our light data from, And what we want to do is we probably want, there's a couple different ways we could look at doing this, right? And I don't know which one is the smarter way to do it, but what I assume we more or less want to do is produce a composite light vector that's just the result of blending in the various lighting directions that we have, right? And so we kind of want something that's going to, again, I really just don't know. There's different ways we design. I don't know which way is the smartest way. We could do a separate lighting equation for each light, and maybe that's the smartest thing to do at first. The problem is the directionality of the light at that point is not very well represented. So I kind of think we don't want that. So I think what we probably want to do is treat it as a single incoming light source that is blended, right? And we want to do that in a sensitive way so that we don't end up neutralizing the direction of the light too much. So I think what I might say is if we were to consider the various light contributions here, right? Each one of them has sort of a dot product with our surface normal, right? And so if we were to look and say, all right, let's only collect the light values that actually have to do with the surface facing direction that we have. You know what I'm saying? And start with that. And that, I assume, would give us the information that we need to produce a reasonable blended lighting based on the information that we're getting from our cube, right? I'm not really sure that's right, because the other way to do it is to light as if each face of the cube was an incoming light source that was separate. The reason I don't want to do that, and that I think that's a probably bad idea, is because if you think about what that will create, is it creates fundamentally biased lighting directions, and I think we would see that in the lighting. We would see the fact that as lights move, as things move, it would probably be fine. As lights move, you would see them sort of have this banding effect as they moved around. I think that would create artifacts that would be objectionable. That's just my gut feeling. I'm not sure. Whereas if instead we take the lighting directions and say how much light's coming from this face of the cube, how much light's coming from that face of the cube, combine those together to produce a average light direction and an average amount of light. Do you know what I mean? That seems to me to be maybe a better idea. I really don't have any more intelligent thing to say than that, I'm afraid. Yeah. So I don't know. That's just what I'm going to go with. I don't know the view direction here, which I kind of need to know. Oh, I do. Fantastic. So I have the camera P and I have the world P, and that's fantastic because that basically lets me do everything that I want to do in terms of a full lighting equation. So what I'm going to do is construct a fairly basic light equation first. We can make it a little bit more complicated as we go. Basically, let me just draw out the basic. We've covered this sort of thing before, but just the basic version that I'll do now. Where is Milton? Again, I ask every time, but no one seems to know. Is there any way to get a Milton that is fixed sampling? The sampling got busted, and now it's hard to draw with it, and I don't know if anyone ever fixed it, but anyway. So what I want to do is I just want to say, look, I've got a surface, and I've got a surface normal, right? I know the world position, I know this P, and I also know the camera position is out here somewhere. So it's pretty easy for me to find a vector that is, how am I looking at this thing? And so what I want to know is when I bounce, when I look at this surface, I want to be able to look up at the light source that are in this direction, right? And so if I reflect this vector off of this surface, I get a direction that is the direction I want to sample the inbound light, right? Now, if we're actually going to compute some more advanced lighting, right? So trying to set this up to do better lighting. The first thing we can do is really, really simple and do a crappy version, which is just take the direction of the light and try to figure out from our lighting probe, which is a cube, right? Try to figure out, like, okay, if I'm looking in this direction and the cube says that I've got these three directions that are like similar to it, right? Blend those together based on how close they are to this, and I'll get some lighting that's like what should be off in that direction, right? But that's 100% specular, right? Because that's just looking at what exactly is right in the direction I'm looking. So that would be like a mirror, right? Now, we won't see any mirrored graphics when we type this in. Well, when we type it in, I'm going to type it in first. We won't see a mirror, but the only reason we're not seeing a mirror is because our light probes aren't detailed enough, right? If we had a really detailed lighting probe that we were sending down, like really, 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 really detailed, right? So this was actually a cube map that was like 256 by 256 on a side. And we did the sampling, we'd get a mirror. That's what we get, because we're going to look and see what's exactly in that direction, right? So, again, like, it's worth noting that equation, it will seem like it's not really mirrored, but it is 100% specular, right? So in order to get a more fair lighting equation that we would want is we can do this calculation and produce what we would see for the specular. We can blend those things together and say, well, we want a specular contribution and a diffuse contribution. The diffuse contribution should be more taking into account the full range of things, right? And so what that should be doing is that should be taking a look at the normal and saying, what are all the faces that the normal can see? So all three faces the normal can see, average those together, and that would be our diffuse light. Because we know that diffuse light is subject to the cosine rule, however, meaning that inbound diffuse light, as you know, right? Remember the cosine rule? This bit here, I drew that poorly, but right. So what we know is the surface of the light as it reflects up. The size of a shaft of light that can come in and hit that surface is proportional to the cosine. And so we actually want to use the cosine rule during that average to say the inbound light coming from that direction can only provide this much light based on the cosine rule, but we would sum it up based on the normal, not on the camera direction, because the direction that the camera is looking would not actually be affecting that inbound light, because we're assuming for a diffuse surface it radiates light out in all directions uniformly in that case, right? So it wouldn't matter. It only matters how the light is falling on the surface, how much it can send back out. Now, this is the kind of thing that I never freaking know, because I just don't spend enough time doing lighting equations. It may be double cosine rule there, meaning we also have to count the sending out, but I don't know. And I'm going to have to go work out the math exactly. But at least there's one cosine rule, which is the surface falling rule. Okay. So first things first, produce that reflection vector. What's the reflection vector? You all should know this by now. I don't want to hear anyone out there who's been watching Handmade Hero tell me they don't know how to compute this, because they do. So you better know how to compute this, right? What we want is we want that vector, right? Here's what we have is we have the camera position and the world position, right? Of the 2 points. We know we can produce this, right? We know we can produce that inbound vector. What's that inbound vector? It's W minus C, right? That's the inbound vector. So we'll call that, like, I don't know, I'll call that the incident direction or something, right? So we have this inbound vector. We know we can produce it. It's just W minus C. Very, very straightforward, okay? We know we have the normal. It's this. So how do we produce this outbound vector? Like, how do we get that? Again, recenter this thing. That produces this, right? If we just assume that this vector here is starting from the origin of our coordinate system, which is just going to be the world position for this point, right? So that's our vector. We want that same vector just coming out of the surface rather than going into it. What is the part of it that's going into the surface, right? What is it? You have a unit length vector here, right? You have a unit length vector. So if I take the the dot product of that vector with the surface normal, I get specifically this length, right? Because it's unit normal. So when I take that dot product, I'm getting this length here. That means if I want to flip this around, right? If I wanted to bring it to here, I would subtract away this much. If I want to reflect it, I would subtract twice that much, right? So I know I want to subtract twice this dot product, right, to flip it around. So if I subtract twice this dot product from the original vector, so if I take I minus 2I transpose n, I need a direction to do that along. We know the direction, it's n. So there's the complete construction. It's I minus 2I transpose n times n. That gives me this reflection vector. I probably want to normalize that, so I'm probably going to want to divide by the length of I to produce a normalized version of this equation. But that depends on what we're going to do next. Maybe we normalize it, maybe we don't. Maybe we normalize it later, I don't know. But that's what we're talking about here, right? So everyone should have known how to do that. No one should have needed me to explain that. If you did need me to explain that, you haven't been watching the series enough, so you need to go back and watch it. Watch those episodes. Use the episode guide to find the part where we talk about reflection vectors. Here, let me help you. Click on watch. Click on reflection. Right? Do it. Watch it. Tons of stuff in here. Right? Find it. I know you can do it. All right. So here's our basic way we're going to produce that reflection. So I want to do exactly what I just said, and I want to produce that here in the lighting system so that when we're per fragment lighting, we're going to use this information. So first we're going to take that camera position, right? And like I said, we want to take the world position minus the camera position. So we do that, and this is our inbound vector. So this is just going to be our inbound vector here, right? So that's the world minus the camera P. What we then want to do is we want to produce this equation out of it. So we're going to want to do that I minus 2I transpose n, n. So what we want to do there is say, let's produce a new one, which is our reflection vector. Our reflection vector is going to be literally the I minus 2 times this I transpose n. So that's going to be like an inner product, right, of I and n. The n, again, is the world normal. So that's the normal of the surface that we're reflecting off of. We're then going to have to multiply that by some vector so we know which direction to move along. Again, that's the world normal. That's that entire top of the equation there. So this here is our reflection vector. Do we want to normalize it? Yes, we probably do. I don't actually know which stuff we put in here for our shaders. I've forgotten by now. So if we look at compile zbias program, I think we have sort of like a boilerplate kind of set of stuff we use for compilation. I don't actually know that. I just think that's true. Let's find out. Yeah, here it is. So here's the global shader code. You can see we can do an inner product here. You can see we do lengths here and so on. Lerp, clamp, right? So in this case, what I would like to do, it looks like we didn't define an inverse square root, unfortunately. And that's kind of a problem. You can see we've got some other stuff defined here, but none of it is really particularly helpful. So what I'd like to do is see to what extent we want to just take advantage of GLSL there. Exactly. So in this case, when I, oops, I'm in the wrong place. I wanted the web browser. There we go. I want to see what they've got for primitives here. We should use, this is a common operation in graphics, we should use theirs. If it's there, it is normalize, is right there. So we're going to call that. And so if I want to do that, I just want to put a define in here that nos a is normalize a, like that. And I think that's really all there is to it. So in here, we want to do a normalize of this. That gives us our normalized reflection vector for now. That's what we'll work with. I'm going to go ahead and compile. In theory, this should do absolutely nothing, but I just want to see if we got any errors there. Make sure that that is doing that is allowed math that I think it is, right? And I don't know. So let's just take a look. We've got an error here. Let's see, undefined variable world. It looks like I typed something in weird. Yes, I did. I was looking at the reflection vector. I'm like, where did I type that? It's like, well, actually, it was in the line above it. OK. So now that we have this reflection vector, we need to do something with it. And like I said, the very first thing we could do is just sample the light in that direction. And all that's going to do is tell us, like, OK, how much light in general would we expect to see if we looked off towards this, in this way. So the way I can do that, right, is I can think of each of these as being a particular direction. And in fact, I can just define these this way for now. And we can optimize this quite a bit in the future. But for now, I'm going to write it out longhand. The lighting west direction, like we know which direction that's coming from, right? It's just that direction, right? That's the sort of the light normal, the direction that the light is coming from. If we looked off in that direction, it's that, right? And the same is true for any of these. I can write all of these as a specific value, right? So in each case, I'm going to go ahead and do that, and you can just kind of see me doing that here. And finally up and down. And so once I have normals in each of those directions, I can do some pretty simple blending if I want to. I can do just some kind of a radial blend on these, for example, or whatever I really want to. So we can think about how we want to blend those later, but for the moment, I'm just going to do a really, really simple blend. And what I'm basically going to say is like the dot product fall off or something will be how I'll blend them together, and that will just be how the lighting contribution works, or something, right? And we'll worry about that as we sort of get further along with our lighting. Okay, so for each of these, what I want to do is basically have a maybe utility function here, right, that I can use that gives me back the light contribution. So this here would basically be something where I would, get irradiance or something like. And that, what we'll do is when we sample these textures, right? In fact, maybe I'll just do a pound define, so it can actually just be inlined in here. What I want to say is like, all right, so for a light, whatever it is, and a light normal, right? So like or a light value and a light normal or something like that. If I want to sample some direction, so like the sample normal, compute what that should be. And I guess if I do it this way, actually, I can just make it a function. There's no real reason not to, so maybe I'll do that. So in this case, I'll just say, all right, you got a light value, you got a light normal, you got a sample normal, and I want this thing to return the light value, right? So in this case, the result, I guess, is something, and I return it. And that something is going to be this equation, right? So it's basically like whatever the light value is, expanded out to be a real light value. So that's an actual intensity light in floating point. And then I just want the inner product of light n sample n. That tells me the fall off, right? And furthermore, I need to clamp that between 0 and 1 because I don't want it to ever be negative. So I just take the cosine fall off, I use that to apply how much light is supposed to bounce off this thing, and then that's it. Right? That's it. That's the light. Happy birthday. And that's the end of it. All right, so if I was to then sample the irradiance here and instead replace, right, all of my light data summations with actual, irradiance calculations here. So I say, all right, there's light west n, and then my r, my sample direction, right? And just nuke all of this. Then now what I should be able to do is sum all my lighting up by just, doing east, south, north, down, up, right? And as long as I use the correct direction paired with the value in question, now I am actually computing a really crappy but still not completely ridiculous lighting equation off of the light probes that are in this nominal voxel or whatever the heck is going on. So now when we look at the voxel, we should see some degree of lighting occur that has to do with the direction that you're facing. Looking at it here, it looks more like it's positional, so we've got some bugs, but that's where we're at. All right. So now let's see. What did I screw up? Let's fix everything, right? So again, world P, camera P. That is what we want. That's the inbound vector. The reflection vector is just that vector itself, right? Minus 2 times the inner product with the normal times the normal. So that should bring it up. And we normalize that. That seems good. Here's all of our light normals. I think they're correct. Here's our summing. Irradiance is probably the wrong term here, but oh well. So let's see how bad this is. Did we do something wrong here? I'm not sure. Anyway. So we're taking the dot product between the light and the normal, and we're clamping that between 0 and 1, which I think should give us the correct blending factor there, right? And so I'm just trying to figure out now, what I really want to find out now is just like, why is position involved at all, right? Because we're stuffing the voxel at every point. So why would the world P, why would that matter at all? Oh, you know what? No, actually, that does make sense. Because as we get to the middle of the screen, we're looking the other direction. So you know what? That actually makes perfect sense. You know what? That's exactly right. So no, I totally take it back. Because remember what I said originally. This is a mirror now. It is literally all of our surfaces are mirroring the incoming light. Now they have a texture applied as well, so it's a mirror that is actually colored with a pattern, but it's a mirror still. And so it's going to look at the light that's incoming from a direction and repeat it exactly. It's not going to sum it at all, right? And so as we look across the screen, eventually we're looking in the other direction. This was all looking west, right? And then now we're looking east. And as we stop and start looking east, yeah, we do expect that fall off to occur. Now, what I don't think is correct is the fall off, I feel like, should have been gradual. So it should be getting gradually dimmer, and it should have like it is tapered a little bit, but not that much. Like, so that fall off rate seems like it might be wrong, but it's hard to really say because cosine fall off is a sine curve or cosine curve, you know. So you do have to wonder a little bit about that, and I guess that part I'm not really sure. So kind of a little bit tough to say. I'm not super prepared to say that it's actually wrong, so hard to say, right? But for example, now if we were to create sort of a more complicated lighting equation, we could blend those together. Let's go ahead and try lighting it from different directions and make sure that that actually creates what we expect it to create. So if I go to the lighting code, and in here now I just start to fill in different things. So let's say I fill in east now. And now we should see the opposite occur. It should be the east side of, of the reflections that we see. And just to make sure that's right. Again, just trying to check that lighting equation to see if it actually works. So that looks good there, right? That's what we would expect to see, I guess. So there is one thing also I think is wrong, which is that I feel like that world P is sent down from the wrong place, though. So you can see this is a slight bug we should probably fix at some point. When we're computing our lighting, we're computing it with the debug camera when the debug camera moves. You can see that happening here, right? And that's really not what should be happening. We should be computing it just with the game camera. So this world P is getting sent down wrong, I think. So that's kind of an issue as well, but we can kind of deal with that later. All right, so let's try some other ones. Let's try a northward light, and then a southward light. Oops, southward light first, sorry. Excuse me. So now what we're expecting to see here, so a southward light is going to be coming from negative y. So it's coming from this direction. So what we expect to see now is anything facing that direction, like these, should just get it to totally, right? Well, I mean, we're kind of boinking downwards, I guess, but let's see here. And then, yeah, as I tilt the camera, so that seems sort of wrong to me, actually. Like as I'm looking, I feel like what I'm seeing is that it's actually coming from the wrong direction. So south should be behind us. It looks like that reflection is sort of wrong. That doesn't feel right to me. The southward one is, so it's because it's coming from, right, -1. And so as I got down there, that reflection should have been looking out. So I do think we've got a bug here. I'm not sure what it is, but I do think we've got one. That doesn't look right to me. And again, that could be because the debug camera part of things is wrong. I'm not sure what's being sent down there for that value, so maybe I'm overreacting here, but I do think something's a little fishy with that. It doesn't seem correct to me. If you assume that that lighting what would that be from? And of course I can't step into it because it's on the GPU, so you always get that nice aspect of it. So if you take a look at the light normal and the sample normal there, the sample normal So hold on a second. Let me make sure I'm passing all these correctly as well. You can see that is fine, right? So that just should be correct. The south normal looks fine. Yeah, so I don't see exactly what's wrong with that. Um, so I guess I can't come up with a hypothesis for why that would be doing that. And so we may have to save that for next weekend because I can't think of anything quickly offhand why that doesn't appear to be lit correctly, in my opinion, though. Um, just looking at what's happening there, it doesn't make a lot of sense. Oh, or does it, though? I don't know if the normals are correct for our sprites. You know what? Our normals are probably wrong for our sprites. That's probably all it is. So looking at it here, because I'm looking at the cubes, and the cubes are exactly right. So I think our normals are just wrong on our sprites right now. That's almost certainly what the problem is. All right, so forget the sprites. The sprites are wrong. Let's just not look at those, and we'll go fix the normals on our sprites some other time. So no, I think that's right. That actually does look right now, so that's fine. I was gonna say like I can't come up with anything, and the answer is because yeah, we're not looking at the wrong thing. All right, so let's try the northward light, and I'll just verify the rest, and then we'll end for the day. So I think we're all good here, and we can then go forward with the lighting as we would have normally. And I'm sure fixing the normals on the sprites won't be a huge deal because we probably just never set them up right in the first place. All right, so that looks about right. Totally fine there. And now let's just try the up and down. There's the down. Again, looks great. Exactly what I want. So I think we're good. I think we're good. I shouldn't bother restarting the game. I don't know why. I don't just go in and make it so it downloads the thing every time again, because it won't be that slow. Looks good. All right. I think we're good. I'm happy with that. So I think like mostly what we need to do now is just, yeah, like, I mean, and you know what, we could even do one last thing before we finish. So let's suppose we just do like a, you know, something where we do like some different colored lights that come in from different areas. So there's a purple and a yellow light for up and down, right? So now you've got like a purple light coming from above, a yellow light coming from below, and so we should be able to see some kind of like vague application on the cubes of just a uniform blanket light in that regard, right? And again, it's a mirror, right? So we're looking at these things as we tilt around. So as we come head on, right, you can't really see any of it because there's literally no light coming from the azimuth, so you can actually see that black band in there. And so as you look straight ahead, this is like a mirror. I'm looking straight down. It's bouncing right back up and looking at the purple sky, right? And then I come back down here, and the same would be true. Of course, we don't have any bright surfaces for the yellow ground. But like, for example, at a glancing angle, you can see, imagine this is a mirror, right? And you look down at like the yellow sky. So I think we're exactly right. I think that's working working well, and I'm happy with that. So yeah, for now I'm not going to do anything else with it. We're just going to leave it like that, and then next weekend we can start to work on our lighting for in earnest, right? But I think we're good. And I'm pretty happy with where we're at now. That's looking pretty good. Let's close Insight there, and yeah. All right, let's go to a Q&A. And remember, you can use the Discord. There's a pound live channel on the Discord. If you'd like to go over there, you can actually just go ahead and type questions in there, and I take them from Discord as well. I think there's also a link in the bottom of the Twitch page if you're on Twitch. Shouldn't it be I plus as opposed to I minus? Yeah, I think you might be right, because the normal's pointing the other direction already. So it would be a negative value. I think you're right. Oops. Did I close I did close my editor. I don't know why I closed my editor. You know what else is kind of dumb about this now that you mention it? I probably could have just used, there's a reflect function, which I think I could have used. But yeah, I do think you're right, because I did it inbound. I think I did it specifically so that you could just do a plus, and then I didn't do the plus. So I'm not sure why. But yeah, because the world normal's pointing up away from the inbound vector. Unfortunately, I'm not sure why we were getting correct results, though. That might just be bad testing, but I wonder if we have something else wrong, because it seemed like it was reflecting in the correct direction, and that's confusing. Which one is stuffed with So the upward facing light should be, oh, so we should have known that I had that backwards. In fact, that was dumb, because it was a yellow that was coming from the top, not purple. So yeah, we did have that backwards. Good catch. Somebody took my name. Not sure why I glossed over that, because I just was about to do that test, and I did, and then didn't notice. So no, that's all. Yeah, that's correct now. So we had the reflection going the opposite direction. I think that also probably keeps all of the rest. Yeah, so it was just flipped, but otherwise it's good. You can see it still has the azimuth at black, which it should, and we can't see the purple, but that's just because there's nothing to. There's really no way to see the purple. Maybe if I did this, right? There you go. So there's reflecting the purple off of the thing, right? We just don't have a way to look upward, unfortunately. So yeah, I can't actually verify the purple sky very well, but XX to the Big Fox says, I think subtraction is right, actually, isn't it? So the thing you have to remember is it depends what you're doing. So if to go back to the diagram, because either one could be correct, it depends on what you're doing. If I drew, so the way I drew the diagram, it's plus. Oops. And again, you should be able to do this at home. Like I said, we've done this a billion times. So you should be able to do this at home, work it out yourself, and convince yourself that you've got it. But if this is the camera position and this is the world position, here is the normal, right? Then there's two ways I can draw this diagram. One is I can do C minus W, right? And the other is I can do W minus C. So if I do C minus W, what I get is a vector going out to the camera, right? So this is going out towards the thing. That's like the I direction. If I do W minus C, then I get a vector going this direction. The same vector, but they're pointed in opposite directions, right? So this is the one I was talking about, the I, as opposed to, that's probably bad, incident, as opposed to I, right? Either way. So let's suppose I do it with this one. Well, when I take the normal, right, the dot product onto the normal is already going to be negative. Do you know what I'm saying? So if I want to remove that amount, so I dot it onto the normal, it's going to be negative. I want to remove that much from the vector. Oh, you know what? You know what? Maybe I talked myself out of it. Now you guys have me confused. Because when I drew it the first time, it kind of did sound right to me, and now I'm looking at it again. So, but as I'm drawing the diagram, no, it's, I gotta say, this number is negative, and you want to add the normal. You want to go in this direction. So actually, I think I was right the first time. And how did I, and then I read this wrong. Up is purple. So no, sorry, okay. Ignore this entire Q&A. I thought, yeah, no, it was right. Sorry. Sorry, the big fox. But anyway, what I was trying to say is, if you, let me go through the rest of this though, because obviously it's confusing because you managed to convince me I was wrong when I didn't look at it very carefully, right? But no, the upward light is purple, so it's correct. I don't know, and then I thought I saw that, yeah, I don't know. Just totally bonkers. I guess this is what happens when you program on stream. I need more coffee. So if you take a look here at the E, right, let's suppose I did it with that vector. Now when I take the dot product is positive, right? And so if I want to flip this vector around, it's a weirder kind of behavior, because what I want to do is start with the opposite of it, because I want to flip it down here, right? And then if I had done the dot product with the positive version, now I would be adding that in. So you would take negative E plus 2, you know, blah, 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 right? So either you do I minus 2 times the thing, or negative E plus 2 times, you know, E transpose. Does that make sense? So at least I give myself full credit. I did it correctly. I just should have said that instead of assuming that the person who wrote in caught an actual bug. It's right the way it was. And we should see purple sky. So I don't know why. Yeah, I guess that's just, I usually assume I make a mistake when someone catches it rather than assuming I didn't. And maybe that's a bad habit to get into. That's what it should look like. Pretty sure anyway. Where would you put material information for the lighting in the ray tracing part of the algorithm that we still have not plugged in, or in the shader? So my assumption, and I could be very wrong about this, but my assumption is that we will not be able to, we will not have the computational resources necessary to use that information, meaning we cannot actually sample any real material information. So I'm assuming that what we will actually do is we will just use a color value, at best a color value per face, but possibly just a single color value for the entire occluder. And that's just purely for computational efficiency. Obviously, if we didn't have to worry about computational efficiency, we would actually just look up the texture index of the occluder and see what the actual value was at the point we hit, right? But I'm pretty sure there's just no way we could ever afford that. A GPU could. GPU ray tracing could totally. If this was an RTX card, we'd just go ahead and do that. Right? but the CPU. CPU sucks at texture sampling. One of the big reasons GPUs are faster than CPUs at rendering. One of the big reasons is texture sampling. CPUs actually have pretty good math throughput. It's not horrible, right? But their ability to sample textures is freaking terrible. Especially x64. x64 is absolute garbage at sampling textures. If AVX512 ever becomes a thing, then that has gather in it, and then you could start to actually sample textures in a way that might not be extremely slow, but it would still be horrible compared to a GPU, because GPU has special purpose texture sampling units built in. I mean, I don't even know... I am trying to get a image here where that might show it. So I can't really get a good image. I want a die shot. I don't really want that anyway. What I want is a die shot. So what I would like is a picture of this with the texture units outlined. Can I get that? Sadly, it doesn't look like I can, actually. Just trying to find something that would be relatively... So I don't know. I can't even actually load this out here, so I'm not sure. Anyway, doesn't matter. Point being, texture units are a big deal. And CPUs don't have them. That's pretty much the end of the story. AVX512 at least has instructions so that you don't have to downshift and pull everything out to the scalar part of the chip to just go fetch the memory you need for your textures. So it helps a lot, but it's not the same as having texture units. Texture units are way freaking faster than that's going to be, especially when you have so many of them in the on a GPU. So it's just not going to happen. The Big Fox asks, are the AVX load instructions actually fast? Have you tested them? No, I don't. I guess I do have one chip now. I think I have a Core i9 in my dev machine that does have an AVX512 instruction set. But my assumption is that, well, I don't know. I don't want to make assumptions. My assumption is that there really isn't any point in profiling AVX512 instructions yet, because not only are these chips probably not particularly good at AVX512 yet, but nobody has them anyway. So even if the AVX512 load instruction actually was fast, you couldn't ship a game that relied on it, right? So I think AVX512, while it does have instructions that actually make some sense, is not really interesting yet. It will be maybe someday, maybe, depending on how market penetration goes. But you know, I'm just considering it a not particularly interesting thing at the moment. I was going to type in the Big Fox for some reason, which is one of the people who was commenting on the stream. That's not what I wanted. Realworldtech.com GT200. Someone posted this. There it is. Great. Thank you very much. Here is a diagram. Unfortunately, it is not necessarily a modern chip, but it is at least a chip. Do you see where the texture units are on there, right? So you see the memory controllers and the texture units. And just look at how much space they take up, right? I mean, these are the shading units here. They're not even like half the die, right? So the texture unit itself is really, really substantial footprint compared to the ALUs even, right? And so you just, the CPU just, this box isn't there on a CPU. You just don't have it, right? All you've got is this part. And so those texture units, you know, they don't put them on GPUs because they think it's fun. They put it on GPUs because the only way to get the kind of performance that you get out of modern GPUs is to have special purpose hardware that does nothing other than take bilinear and trilinear samples out of textures, right? Because knowing that that is what you do and welding that right up to the memory controller so that it can, like, as fast as possible, get things in, cache them, blend them, and output them in the color format, right? Do the upconvert from 8-bit to float. Having all that like welded right in there is pretty important. Valbus asks, was the PS3's SPUs good at texture sampling? No idea. Never programmed an SPU. Actually. My assumption is that an SPU would be absolutely horrible at texture sampling in the real world. And the reason for that is, how are you going to sample a texture? The PS3's SPUs relies on scheduled DMA to fill its local buffer. It can't do anything from main memory. So you would have to have a really deep texture querying pipeline that has scheduled DMAs quite far in advance and pull them in, and there's not that much space. It's 256K of local space. I mean, you can do it, but it's not the architecture you want. Definitely not, right? Because basically, I mean, another way to say it would be the way that these things work on the GPU is they have very deep pipelines. A shader processor is like processing tons and tons of crap, and it sees it needs 30 different texture fetches. It issues them all, goes processes some more stuff, issues more, and it probably has like a gigantic stack of texture fetches, all outstanding to a ton of texture units. And all of those textures then come back, and then the shader processor then pulls them back in and starts working on the dependent instructions for them, right? And so an SPU just with 256K, where's that depth coming from? Like, it is freaking nowhere to be found, my friend, right? So I really don't, I mean, maybe in the PS3 days because resolutions were so much smaller, like 1080p was like pushing it, right? So maybe in those days, because textures are so much smaller and vertex buffers are so much smaller, maybe you can do something with that. But like, yeah, nowadays, freaking forget it, right? An SPU is just, it does not have the memory throughput, the memory footprint, I don't think, to do anything useful there. And it's not really set up the way you would want, probably. That's just my guess, right? SPUs are much better at localized memory operations. So, for example, vertex transforms, right? Very good. I can take an in batch and an out batch, just concentrate on it, chew through little chunks at a time. That's what it's optimized for. When you think SPU, think digital signal processor. That's what it is, right? And that's what it was best at. Scatter gather, not its thing, right? All right, let's go ahead and wrap it up. Thank you, Anna, for joining me for another episode of Handmade Hero. It's my pleasure coding with you as always. If you would like to follow the series at home, you can always pre-order the game on handmadehero.org. It comes with the source code so you can play around with it. We've got the lighting stuff mostly set up now, and so we're going to start playing with that a little bit more aggressively next week. I hope to see you back here for that. But before I get to it, maybe now would be a good time for you folks out there to play around with it and see what you can do, right? Maybe start putting some little local area lights in there and see if you can sample them properly. Who knows, right? You can play around with it. It's in a good place to play around with right now. So if you're someone who follows along with the source code at home, I would recommend it. See what you can do in advance of next week's episodes. That's about it for today. I'll be back here next week. Until then, have fun programming. I'll see everyone on the internet. Take it easy, everybody.